Hello everyone, my name is Yumna and the paper I'll be talking about today is called Square Attack, a Query-Efficient Black Box Adversarial Attack via Random Search. It was written by Maxime Andriushchenko, Francisco Croce, Nicolas Lamarion, and Matthias Hein. It was published in 2020 at the European Conference on Computer Vision. This paper has gotten a lot of attention. It's been cited over 1,200 times on Google Scholar, which shows how important and influential it is. What are adversarial attacks? Before we get into the specifics of square attack, let's go over some background. Adversarial attacks are small intentional changes made to input data, like images, designed to fool machine learning models. These changes are usually so small that a human wouldn't notice them, but they can completely throw off the model's prediction. Understanding this concept is key to seeing why attacks like square attack matters. In this slide, we're going to talk about types of adversarial attacks. There are different levels of attacker knowledge. In white box attacks, the attacker has full access to the model, including gradients and parameters. These attacks are effective, but assume a lot of access. However, in black box attacks, they are more realistic. We only see the output, not the internals. Square attack falls in this category. When we have a gray box attack, which are in the middle between a black box and a white box, the attacker might know the model architecture, but not exactly the training weights. Now we're going to move on to the challenges with black box attacks. Black box attacks face some unique challenges since they don't use gradients or internal parameters. They rely on just the output, which is the prediction scores as we mentioned earlier. Because of this, black box methods often need a large number of queries to succeed, and they tend to be less effective than white box methods. This is the main problem square attacks aims to solve, which is being efficient and effective despite being a black box. Before we move further, let's quickly go over two important concepts that show up in adversarial attacks, which are the L2 and L infinity norm. In the L2 norm, it looks at the total or overall size of the change, like how much we've changed the whole image, even if the change is small and spread out. The L infinity norm, on the other hand, looks at the biggest change made at any part of the input, like the most single pixel changed. It doesn't matter how small the rest of the changes are, as long as one is big it counts. This makes it useful when we want to make sure that no part of the input is changed too much. Both are used in adversarial attacks to make sure the changes stay small enough to fool the model, but still look normal and unnoticeable to us. You'll see these norms mentioned often in this presentation, especially because Square Attack supports both of them. In this slide, we're going to talk about gradient information. Most white box attacks work by using gradients, that is, they calculate how the model's loss changes when we adjust the input. This tells the attacker exactly how we tweak the input to confuse the model. It's like having a map that tells you which direction to go to make the model mess up. So what exactly is a square attack? A square attack is what we call a score-based black box attack. That means we don't have access to the model's internal workings, like its layers, weights, or gradients. Instead, we only get to see the output confidence scores for each class. These scores are enough for square attacks to figure out how to craft an adversarial example. Now we're going to talk about how square attacks work. So how does it actually work? The attack randomly adds square-shaped patches to small parts of the input, like placing stickers on an image. These perturbations are placed near the boundary of what's allowed, meaning the pixel values are pushed as far as possible without becoming invalid. It keeps testing new patches using random search strategy until it finds one that makes the model misclassify the input, all without needing the gradients. So why is the square attack so effective? Square attack is highly effective for a few key reasons. First, it's immune to gradient masking, which is a common defense against gradient-based attacks. Because square attack doesn't use gradients at all, this kind of defense doesn't stop it. It works under both the L2 and L infinity norm constraints, which are different ways of measuring how strong the perturbations are, as we mentioned before. This method also comes with convergence guarantees. That means it's mathematically proven to keep getting better over time as the search continues. Now, what's really impressive is how well it performs in different scenarios. The author tested it on MNest, Cephar10, and ImageNet, covering simple to complex image tasks. Across all these cases, Square Attack outperformed other black box methods, both in terms of success rate and how few queries it needs. This figure from the paper shows just how efficient square attack is compared to other black box attacks. The chart compares the average number of queries needed to successfully fool three different ImageNet models. As you can see, square attack consistently requires fewer queries than the others by a large margin. This is especially impressive since it's a black box method, meaning it doesn't have access to the internal details. The results highlight how effective random square shape perturbation and search strategies are in making the model misclassify with minimal effort. To understand why square attack is such a useful approach, we need to first look at the different types of black box attacks that came before it. Some of the earliest methods tried to estimate gradients by making small tweaks to the input and observing how the model's output scores changed. This worked, but it was costly. It needs a lot of queries, especially for images. Later, researchers worked on making this process more efficient. They used strategies like PCA to reduce the number of directions to explore, or methods like bandits that used feedback from the model to guide the search more intelligently. Other attacks moved away from gradients completely. For example, gen attacks use genetic algorithms to evolve inputs over time, while Simba explored one input direction at a time. These approaches helped reduce query costs but weren't perfect. There were also attacks that focused on the infinity norm and used square-shaped patches in fixed grids to apply changes. Square attack builds on this idea but improves it by applying those square patches randomly, giving it more flexibility and making it harder for the model to defend against. Finally, there are attacks that only use the final predicted label or rely on substitute models. Square attack avoids those complexities and finds balance by just using methods output scores without needing internal access. Let's begin by understanding what adversarial examples are. When a machine learning model sees an input like an image, it doesn't just guess, it calculates a confidence score for each possible label. Whichever the label has highest score is the one it predicts. Now, adversarial example is just a slightly altered version of the original input. The change is tiny, often invisible to humans, but is carefully crafted so the model gets the answer wrong. And in untargeted attacks, we don't care what wrong label the model chooses, as long as it's not the correct one. That's the basic idea behind adversarial examples in this context. This section sets the foundation for the rest of the paper by showing what kind of problem the square attack is trying to solve, how to create small, stealthy changes that successfully fool the model. Now let's take a look at what makes these changes realistic. We don't want the modified input to look completely different. That would defeat the point. So we control the size of the changes using a p-norm, which is a mathematical way of saying keep it small. We also make sure the new input still looks like a valid image. For example, its pixel values can go out of the bounds. There are two main goals of launching an adversarial attack. One is untargeted, where we just want to confuse the model into predicting anything except the correct label. The other is targeted, where we try to make the model confidently choose a specific incorrect label. To guide this process, we use a loss function. In untargeted attacks, this function helps us reduce the model's belief in the true label and increase its belief in the wrong one. The smaller this loss gets, the more likely the model is to make a mistake. And that's what we're aiming for in attacks like square attack. Now let's take a deep dive into algorithm 1 from the paper. The algorithm is built on something called random search. That means it doesn't use gradients or internal knowledge of the model. Instead, it works by randomly sampling changes to the input, checking if those changes make the model more wrong, and keeping the ones that help. Because it doesn't depend on gradients, it's especially useful for black box attacks. Let's now walk through the exact steps of how algorithm 1 works. Step 1, we have the initialization. So we start by creating a slightly modified version of the input, using a square patch. Then we compute how wrong the model is, which is the loss. And we set our step counter to 1. Step 2 is the iteration loop. We'll now repeat a loop up to n times, or until we successfully fool the model. Now we have step 3. So at each step we decide the size of the square we'll use. The squares start big, so we make large changes early, then get smaller over time for fine-tuning. For step 4, we sample the perturbation. So we randomly generate a new square patch to add to the image. The way we sample depends on how or which norm we're using, so the L2 or the L infinity. For step 5, we apply the patch to the image and then make sure it's still valid, meaning the pixel values stay between 0 and 1, and the total change doesn't exceed our allowed limit. And for step 6, we compute the loss. So we check how wrong the model is on this new image. That's our new loss. For step 7, we either accept or reject. So if the model is now more confused, meaning the loss got lower, we keep the new image. If not, we toss it out and try something new. And for step 8, we update counter. So we move to the next step and repeat the loop. And that's it. The algorithm keeps trying smarter and smarter square patches until it successfully tricks the model, or until we hit the limit of queries we're allowed to make. Now we're going to move on to algorithm 2, which describes how the L infinity version of that square attack works. So instead of changing individual pixel one at a time, this method modifies square-shaped regions of the image. Each shape placed randomly and filled with a value, either plus 2 epsilon or minus 2 epsilon. We use the 2 epsilon so after clipping, the patch still reaches the maximum allowed change in the final image. This helps push the input as far as possible without breaking the allowed limits. So this part of the algorithm is about constructing the actual noise that gets added and doing it in a way that's controlled. Now let's walk through the algorithm 2 step by step. Step 1. First we initialize a blank tensor. It's the same size as the input image, but everything starts at 0. This represents no change yet. Then we randomly pick a location in the image to place our square patch. We make sure the square fits entirely within the image. For step 3, we move through each color channel. So for RGB image, we do this for red, green, and blue individually. For step 4, for each channel, we randomly decide if we're going to increase or decrease the pixel values. So we choose either plus 2 epsilon or minus 2 epsilon. And for step 5, we fill the selected square area in that channel with the same value, either all positive or all negative. This gives us a clean, consistent change in that region. The final result is a patch that strongly changes a small part of the image. This patch will be added to the input during the attack, and after clipping, it will still be valid but powerful enough to fool the model. In this slide, we're going to talk about algorithm 3. So this part of the square attack shows how the method works when we're using the L2 norm. Instead of making big changes all at once, this version spreads changes smoothly over the image. The idea is to treat the change we make like energy. The algorithm picks two small square areas of the image, one to add energy to and one to take it from. This way we stay within the total allowed energy limit. The changes aren't just random noise. They use a special pattern called eta, which has both bright and dark spots to balance out the effects. This helps the attack stay subtle while still tricking the model. Now let's walk through algorithm 3 step by step. In step 1, we figure out how much we've already changed the image so far. This helps us stay within the total epsilon squared energy limit. Then, in step 2, we randomly pick two small square areas in the image. One square is where we'll add the new patch, and the other is where it's going to be cleared, like shifting energy from one spot to another. In step 3, we're going to check how much room we still have left before hitting the change limit. And in step 4 is where we're going to bring the eta, and we normalize it so it's ready to be scaled. And step 5 happens for each color channel. We randomly choose either brighten or darken the square. Then we blend in the structure eta patch into the first square. Then we calculate how much energy we can use, and then clear the second patch and apply the updated one. Finally, we build the full update and apply it to the image. This gives us a more powerful adversarial example, one that still follows all the rules. Now that we walked through the algorithm step by step, let's connect it to the perturbation and how it actually looks like. Here's the visual of the eta patch that plays a key role in the L2 square attack. This patch has a unique swirl pattern with opposing bright and dark regions. And it's not just for show, it plays a key role in how we redistribute energy within the image. In algorithm 3 in step 4, we use this patch when shifting energy between two regions as we mentioned before. One region gets updated with this eta pattern and the other gets cleared. The idea isn't to add more noise but to redistribute what's already there, which keeps us within the L2 limit. This structure makes the attack more efficient and precise, especially in high-dimensional data like images. Now let's compare what the perturbation actually looks like. In figure 3 in the paper, the L2 attack is shown on the right. The changes are smooth and spread out. You might not even notice them at first glance. That's because L2 norms limit the total energy of the perturbation. In contrast, the L infinity attack in the middle applies sharp, blocky changes that are much easier to spot. These push pixels to their maximum allowed change, making them more visible. So this figure really highlights the benefits of the L2 square attack because it's subtle but still very effective. Why square attack works. So this section of the paper explains why square attack is so effective. The authors don't just say it works, they support it using both math and experiments. They focus on the L infinity attack where the changes to each pixel is limited. What's interesting is that even though it doesn't use gradients, it still works reliably by using structured random search and leveraging how neural networks operate. Let's look at how they back that up. The first explanation comes from theory. The authors show that even with random updates, the attack gets closer to success with each step as long as the steps aren't too large and they go in useful directions. The math proves that the average slope of the loss function gets flatter over time, meaning you're moving towards a solution. And even if the exact randomness used doesn't match all assumptions, they show that a very similar one still fits the theory using the Khinchin inequality. So why do square patches work so well? It's because they match the structure of convolutional neural networks. CNNs use square-shaped filters when scanning images, so if your patch is square too, it disrupts the network more efficiently. The author proves this mathematically. For a fixed number of changed pixels, square patches activate more filters than random or rectangular ones. That makes the attack stronger and more effective. The authors didn't just guess these design decisions, they tested them. In Table 1, they ran an ablation study to see which versions of the attack needed the fewest queries. Using square patches performed better than rectangles or scattered pixels. Changing all RGB channels the same way worked better than random colors. And starting with neat vertical stripes led to faster success than random noise. Each of these choices make the attack more efficient, which is critical in black box settings. Okay, so now we're going to talk about section 5 in the paper. So section 5 is all about showing that square attack isn't just theoretically sound, that it's practically effective as well. The authors run several tests to prove how well it performs, both against common black box methods and even compared to powerful white box attacks. They focus on how often it succeeds, how many queries it needs, and whether it can handle robust models with strong defenses. In this test, the author tested square attack on large-scale ImageNet models. They used 1,000 images and allowed each attack up to 10,000 queries. Table 2 shows how well square attack did compared to other black box methods. For example, on ResNet 50, Bandits failed 1.4% of the time and needed around 727 queries on average. But for square attack, it had 0 failures and needed only 73 queries on average. Now let's see how square attack performs when the number of queries is really limited. In this test shown in figure 4, the authors only allowed up to 200 queries. That's not much, especially for black box attacks. But even then, square attack started outperforming the others early on. It didn't need hundreds or thousands of tries to work. It was effective almost right away. This shows one of square attack's biggest strengths. It's not just accurate, it's fast, even in tight query settings. Now to make sure square attack's results aren't just luck, the authors ran another test. They only looked at the cases where all attack methods were successful. So this removes any advantage from one method working more than the other. Even in this controlled setup, square attack still stood out. It needed 30 to 50% fewer queries to get the job done. This proved that its efficiency isn't just luck. So the authors wanted to see if square attack can compete against white box attacks like PGT, which has full access to the model. which it did. On robust MNIST models, square attack matched or even outperformed PGD, as you can see in table 4 right here. In this test, the author targeted models that use gradient masking, which, as we mentioned before, is a defense technique that throws off white box attacks by hiding or distorting gradient information. PGD, which relies on those gradients, didn't have much of an impact. But square attack doesn't need gradients at all, and as a result, it was able to break the models. In this slide, we're going to talk about square attack versus CLP and LSQ defenses. Table 6 here shows the strength of square attack on models with strong defenses like CLP and LSQ. These defenses are typically very difficult to break. While methods like PGD often struggle to make an impact, square attack is able to bypass these defenses efficiently. On the CLP MNEST model, for instance, PGD leaves the model at over 60% accuracy, but square attack cuts it down to just 6.1%. To conclude, square attack stands out because of how much it achieves with such a simple strategy. It doesn't rely on gradients or internal model details, yet it consistently beats or matches the performance of more complex white box attacks. It's especially effective against models protected by gradient masking. So in the end, square attack isn't just a strong black box attack. It's also a reliable tool for evaluating the true robustness of machine learning models.